Okay, my Diffie little babies. We are back, Chapter 3, Section 3. Let's look at another application for some of the basic differential equation techniques that we've learned so far. For Section 3, we're going to look at the topic of heating and cooling of buildings. So the idea is, of course, if you think about, let's say, large commercial buildings, when you're choosing to install some type of central air and heat furnace, some type of heating or cooling mechanism, and you're trying to figure out, well, how long would it take to cool a building or heat a building based on the temperature outside. There would obviously be quite a lot of factors that would play a role in the rate of change in the building's heat over time or cooling over time. But either way, we are still dealing with rates of change, right? Rates, in this case, it's the rate of change of the temperature over time. So if you're dealing with rates of change, you're dealing with derivatives. If you're dealing with derivatives, you are dealing with differential equations. And what we're going to do is we're going to start off just really basic. We're going to list just some ideas, right? Some categories. We're going to try to categorize some things that would affect the temperature of, let's say, a building, the temperature inside of a building. All right. So let's start. Let's think about if you were thinking about things that would increase the temperature in a building, right? So if we were trying to jot down things that would increase the temperature in a building. Well, lights. Lights would increase temperature. Obviously, if you have people, we emit heat, so we would increase the building's temperature. If you have machinery going on in the background, this would also increase the temperature. And let's also think about other things that would affect the temperature in a building. Okay, so let's think about the air conditioning units, right? AC, or the heating system, right? This would also affect the temperature, or in this case, regulate the temperature inside of a building. And finally, another category might be, well, what's the temperature outside? Now, what we can do is, and we don't want to have a large quantity of variables in our differential equations, especially not right now. So what we're going to do is we're going to take each of these categories and lump them together as one function. Right? So we're going to call this first category H of T. Right? H of T, this would be the rate of temp, and I'll write this on it's already written on the next page, but H of T is the rate of temperature increase per unit of time. Right? So in this category, all of those things are increasing the temperature in the building. Lights, people, machines, etc. This next category, category 2, let's label that as U of T. And we'll say that U of T is the rate of temperature increase or decrease per unit of time, right? So things like air conditioning and heating. And finally, the outside temperature, we're gonna, since that will also vary over depending on the time of year it is, we're gonna just label that the function M of T. And this would be the temperature outside, say, at a given time. All right, so I'm going to go ahead and go to the next page, and we're going to, you should probably pause it, right? Because I realize this is a large drop of text all at one time, but it's a whole lot easier to it's just a whole lot easier to have it all here without me writing it in real time, and now I can just discuss it. So look, if you have to pause the video, feel free to pause it and write everything and then press play. So ready, we've already discussed many of these. So H of T, those were the lights, the machines, the people. This is the rate of the temperature increase per unit of time. And what we're going to assume is that obviously this is always positive, right? I mean, because if it's in this category, it's always contributing to the increase of the temperature inside the building. Whereas U of T, now this is the rate of temperature increase or decrease per unit of time. Now in this category, you could have negative values or positive values, because you could have AC on that's decreasing the temperature, or heat on which is increasing the temperature. Now T of T, or the way we're going to think about this is the temperature, capital T, temperature, inside this building that we are considering at a given time. All right. We've already discussed that last category, M of T, which is just the temperature outside a building at a given time. Now, at some point in time, if you want to, we're going to start with very basic. We're going to think about the rate of change in the building's temperature due to the temperature outside, right? So in this case, what we have here is, let me read it off to you. So we have some constant K, right, that we'll chat about in just a second, some constant K. And then let's think about what we have multiplied by M, which is the temperature outside, minus T, which is the temperature inside, right? And how the rate of change in that building's temperature due to the temperature outside. That's the way we're going to think about our rates of change. And again, this just kind of stems from Newton's law of cooling, but we've chatted about that in the past. And let's chat a little bit about this K that popped up. What is this constant K? So it is a constant. It's a positive constant. And the way we're going to think about it is, well, each building, depending on how many windows it has, depending on the types of insulation, every building, don't you agree with me? Every building is going to be affected by the outside temperature differently, because depending on, if you have more windows or less windows, or more insulation or less insulation. So each building is going to be affected by the outside temperature differently. So you can think about this K value is going to vary with each building. How's that? Okay. Now, what we assume, though, is once the building, this value itself is not affected by the temperature outside. It's not affected by the temperature inside, etc. In other words, it's due to the nature of the building itself. It's because they installed X amount of windows and X amount of insulation, or Y amount of insulation. That is the constant that we're considering here. Now, I'm not going to go into this idea of the time constant in too great of detail, but if you take the reciprocal here, right? So 1 over K, then what we're going to label that as the time constant, right? Again, and each building is going to have its own time constant. And if I had to loosely define it, I would say, look, the time constant is how long a building with no air conditioning, no heating, will change temperature significantly, right, or substantially. That's that. Can we leave it at that? Let's just assume that, look, based on the design of the building, the time constant is just how long will it take for the temperature change, temperature to change significantly, okay? Either heating or cooling. All right. So where do we go from where do we go from here? So we have some basic vocabulary, and we'll refer back to that vocabulary. But we still don't have a differential equation, right? Okay. So what I want to do is I always have a choice at how long do I spend building up the the math to get to the formula that we're going to use, right? It's I don't want to just blindly give you formulas, and nor do I want to use up the time that we have on mathematics that you could cipher through fairly easily. So what I'll do, if you allow me, is we'll go through this just very quickly. I won't go through all the details. But the idea is, since we have all of those factors, H, U, M, and then the K, all of these things are affecting the temperature of a building. So if you are interested in the rate of change, right, that dt of dt, the rate of change of the temperature inside a building over time, right, then the differential equation can be written as follows. So we just have K multiplied by the temperature outside minus the temperature inside, plus H plus U. Okay, so you understand that that's what I have right up here. This is the differential equation. And now the job of this class is to solve, right, the differential equation. So the way that we're going to do this, I did this slightly different than the way the author did it, but it is this above differential equation, it is linear, and that if it is linear, that means that you can go through and rewrite it. Okay. All right. Now the way I've rewritten this differential equation, what I want to do is I want to show you how you can the way I want to start here. Okay, notice that I've eliminated all the of t's, right? H of t, U of t, just to free up some space here. Now the way that the author of the textbook approaches this is they lump a few things together, right? So in other words, if you look at the right side of this equation, the author just calls all of that, just labels the sum of all that, I believe, Q, right? Probably Q of T. So this is the way the author treats it. But what I want to do is, since it is linear, you can rewrite it. You can solve it, right? As long as you can find that that integrating factor, it'll be U of t for this case, and in this case, U of t would just simply be e to the power of kt. So now, what am I going to do? I'm going to jump to the results. But if you were to go through and distribute this integrating factor and go through all the steps of that we use when we're solving linear differential equations, you would see it would not be that bad, right? It would not be it would be cumbersome, it would take time, but you would be able to get to where I'm about to take you. Are you ready? So what is the result? What is the solution to that differential equation? Well, I'm about to write it. So the formula that we're going to use over and over again for this section is as follows. So we have T of T, right? That's the solution. The time, the temperature of a building at a given time is going to be equal to E to the negative KT. And that is going to be distributed amongst the integral of e to the positive kt. And now comes the sum of all of those three categories. So it's going to be k times m of t plus h of t plus u of t. And now let me close off everything. We want to integrate this with respect to t. And forgive me for running out of space, but it's going to be plus c. Okay. Now I have this rewritten a little bit smaller font on the next page, but I think you get the gist. Okay, so what types of questions are we going to be asking? So I have two examples that I want to go through. The first example doesn't provide any real values. So I want to actually, in this case, I want to read the second example so I can at least show you the types of questions that we're going to be answering. And then I'll probably pause the video since we've worked through the vocabulary, and then the next video will just solve those two examples. Ready? So this is the type of questions that we want to be able to answer. Are you ready? So we have, on a mild Saturday morning, while people are working inside, right, so inside a building, the furnace keeps the temperature inside the building at 21 degrees Celsius. All right, now at noon, the furnace is turned off and the people go home. All right, so, okay, so at noon, they turn the furnace off and everyone goes home for the day. It says the temperature outside is a constant of 12 degrees Celsius for the rest of the afternoon. Okay, so right now let's go ahead and well, actually, let me finish reading it, but then I'm gonna collect the information that we need to solve the question in the next video. It says if the time constant for the building is 3 hours. Okay, so remember the time constant, we define that as 1 over k is equal to 3 hours. Now it also said the outside temperature, remember that we labeled that M of T, is 12 degrees Celsius. So, okay, so with a time constant of 3 hours, when will the temperature inside the building reach 16 degrees Celsius? Okay. Then it says, if some windows are left open and the time constant drops to 2 hours, when will the temperature inside reach 16 degrees Celsius? All right. So remember, it said at noon, everyone goes home and the furnace is turned off. So if we're going to assume that the furnace is turned off, that would mean that the U of T is 0. Right? It's no longer contributing to the temperature. And we're going to assume that there's no other machines, and we'll assume that the lights are turned off. And I think what they're really trying to get at is since all the people go home, they're also trying to tell us that H of T when it's noon is also 0. Okay, so when we come back from this next video, we're going to take this information and we're going to use that T of T formula, and we're going to see if we can answer this question. See you in just a second.